So we'll start the meeting. So today's first speaker is Thomas from George Mason University, and the title is Introduction to Character Varieties.
Hi, everyone. I'm Sigol. I'm a PhD student in George Mason University. My advisor is Professor Sean Lawton. He is also giving a talk on Wednesday. Sorry, I think it's Thursday in the Eastern time, Wednesday. So my research area is I work on character varieties. So the first talk of my two talk that I'm giving today, I'll talk about introduction to character varieties. And the objects that I work with in my research is character varieties. And tomorrow I'll talk about what my research is based on, which involves understanding the dynamics of actions, group actions on character varieties. I want to thank the organizers for giving me the opportunity to give this talk. Okay, so the structure of the talk is I'll start. So I want to start with the definition of varieties. So if there are people who are already familiar with it, please bear with me for a minute. So I'll briefly discuss, define, or explain varieties, and then I'll talk about character variety, what a definition and its construction, and then I'll go over an example, and I will discuss some results about generators of how to calculate or compute character varieties of specific in a specific case. Okay, so first, algebraic geometry, probably everybody knows it's a field that connects algebra and geometry. So what we do is we use algebra. So the idea of algebraic geometry is we try to study geometric objects using algebra, right? So very loosely speaking, we can think of the objects that we study as graphs or higher dimensional graphs or n-dimensional graphs, for example. So what is, for example, if you want to think of something like you can visualize intuitively like a circle, it's a graph, right? It's an and what is a graph? It's a zero set of a circle is a zero set of a polynomial, right? It's given by the equation x squared plus y squared equal to, the unit circle is equal to 1, which means you can think of it as the zero set of the polynomial x squared plus y squared minus 1, right? So that is that's we can think of sets that are simultaneous. We don't have to just restrict to one polynomial. We can take a collection of polynomials and look at the simultaneous zero sets of those polynomials. And those are what we, in some sense, that is kind of what variety, the objects that we want to study. And like I said, since they are given by polynomials, and we can connect these polynomials to rings, right? So these polynomials are elements of polynomial rings, right? So there is a way to assign a ring to these objects, and then using the algebraic tools, we can study some properties or geometry of these objects that we want to understand. So the objects that we study in algebraic geometry are called varieties, and the rings that we assign to these varieties are called coordinate rings. So I'll explain, I'll define what varieties are and what coordinate rings means. Okay. So keeping in mind the example of the circle that I was talking about, a circle is it's a collection of points, right? So, and these points come from some space, right? So first we want to have a space, underlying space, that from where we take these points. Okay, so we define something called affine space. So for this talk, I'm going to define, I'm going to restrict to the definition with field which is algebraically closed. So suppose K is an algebraically closed field, and then we just take the set of n tuples of this field K, and that is what we call the affine space, and we use the notation A superscript n to define the affine n space. Okay, so this is our underlying space, and this is where we take the points from. Okay, and then we look at and then what is the polynomial ring that is related to this space is we have so if we have n points and we are taking n points, we want to look at a polynomial in n variables, right? So that's the maximum number of variables that we can plug this point in, right? So this is the polynomial ring that we are working with. This is it's the polynomial ring in set of all polynomials in n variables over the field. Okay. Okay. And then now, how do we formally define these zero sets? So suppose we take a subcollection of this polynomial ring, okay, and let's call it T. And we define the zero set of this polynomial to be Z of T as all the points in this affine space, all the points in the affine space such that it's the zero of, such that it is the zero, such that the point is zero for every element in the subcollection T. So it's basically the simultaneous zero set of all the polynomials in the subcollection that we are taking. And in the case, if there is, so if we take any subset of this affine space, it is called algebraic, or it's called an algebraic set if there exists a subcollection of polynomials such that this set is the zero set of that. So if it is in the analogy that we were talking about, if it is the graph of some collection of polynomials or intersection of graphs to be more precise, then that set is what we call an algebraic set, okay? Because this is the object we kind of want to study, right? So we have a space and then we have something called algebraic set, right? So now we want to add some additional structure to it, and so we want to make it into a topological space, right? So these definitions I was referring from Hartshorne, algebraic geometry by Hartshorne, if you're interested in looking at the definitions later on. Okay, so now we assign some topology, right? So so the topology on this space is called Zariski topology. So since we want to study this algebraic set, so we call the algebraic sets to be the closed sets, and these are this is the topology, right, of on the space, and it's not necessarily Hausdorff always. Okay, and now now let's look and. Now, if X is a topological space and Y is X is a space and Y is a subset of X, then this space is called non-empty space, a subset of X. Then Y is irreducible if it cannot be written as a union of two closed subsets of Y. Okay, where Y is any or X is even any subset of AN with the subspace topology. Okay, so the way Hartshorne define an affine algebraic variety is basically any algebraic that is irreducible. So it's an irreducible closed subset of AN. Okay. Okay, so now I mentioned earlier we assign a coordinate ring to these varieties, right? So let's go back once to here. So I mentioned here that we are looking at graphs, right? Or we are looking at the zero set of polynomial, right? So if the varieties are zero sets of polynomials, when we go to the ring, polynomial ring, we kind of want to look at naturally, what is the natural way to what is one natural condition that we would want is we kind of want to look at the set where, or look at the ring where the polynomial is also zero, right? So what is a natural way to look at make something zero in the polynomial ring is actually making it quotienting it out by those elements, right? So for any subset of AN, say y, we define the ideal of y to be the set of all polynomials such that y is the zero set of those collection of polynomials. Okay, and we take the so even if it is a subset, if so, I mentioned here we took the just a subset here, but if T is any subset, then the zero set of T and the zero set of ideal generated by T is going to be the same. Sorry, which is why I have this ideal. We have the notation I, so it's basically the ideal generated by all the polynomials, which gives y to be the zero set of that collection. Then we define the coordinate ring A of y to be the quotient of the polynomial ring divided by that ideal of y. Okay. Any questions so far? So that's basically, we have the defined space, we have a algebraic set, and then we define the topology, Sierski topology with the algebraic sets of the closed sets, and then we assign coordinate ring to these to a subset of a affine space. Okay. So now, before I go into the definition of character varieties, I want to say briefly why we care about character varieties and why we study these. So character varieties are actually varieties which is defined in a specific way, which I will get to in a minute. And they are interesting because they are central in studying moduli spaces, and they come up in mathematical physics, especially when in the study of Higgs bundle, and people, not theorists, are interested in character varieties. So there are different areas that where character varieties are used, and it's also interesting because it also brings together some of the different areas or disciplines like geometry, algebraic topology, then number theory, and so there are different areas that it's very rich in connecting these kind of different areas. So there are different people, mathematicians who are working in different areas who are interested in character varieties for different reasons. Okay. So now defining a character variety. So how do we define character variety? So a character variety has two components. First is gamma, a finitely generated group, and G, an algebraic reductive group. So an algebraic group is a group that is also a variety, such that its multiplication operation and the inversion operations are actually morphisms in the varieties also. So it has a group. It's a group and a variety such that the operations are compatible. The group operations is compatible with the variety structure, and it's also reductive. So reductive groups are special types of linear algebraic groups. So I mentioned linear algebraic groups, right? So linear algebraic groups are like GLN and SL, and reductive groups is a special type of. I'm not getting into the definition of the reductive groups now, but there's special type of linear algebraic groups. Okay. And we usually, for this talk, I'm going to work with algebraic groups that are complex affine varieties, which means I'm looking at the algebraically closed field that I'm working with is complex numbers. Okay. So these are the main two components. And now, what is the underlying set or underlying object of the character variety? It's the set of homomorphisms from the set of group homomorphisms from gamma to G. Okay, both are groups. So we look at the collection of these homomorphisms, and we basically are interested in the conjugacy classes of these homomorphisms. So we look at the action of G on this home set by conjugation. And then we take the orbits under this action, and we want the closed orbits of this conjugation action. So we define these equivalence relation rates that two homomorphisms are equal if their orbit closures are intersect, right? And then we look at the quotient. So we quotient out the home set by this equivalence relation, and that gives us the G character variety of gamma. So I will explain. So this is the definition of the character variety. In general, it is the conjugation orbit space where the orbits, we're looking at the closed orbit sets, closed orbits. Okay, so this gives a definition, right? But when we are actually working over complex affine varieties, the groups G, which is over complex numbers, then this character variety is actually coincides with the geometric invariant theory quotient, or GIT quotient. So I'll give a way of how can we go from, so if you're given the gamma and G, how can we actually look at these spaces, like how do we actually compute this as a GIT quotient, okay? So what I'll do here is, okay, I'll start with finitely generated, free group gamma, which is on R generators. So gamma 1, gamma 2 to gamma R. And we take the free group is the set of all words in letters using these letters gamma I to gamma R and their inverses. Okay, and then G is again a reductive algebraic group with the variety structure, with a complex affine variety structure. Okay, then we look at the set of homomorphisms from gamma to G. Okay, and so this is just a set, right? Now there is no structure on the set of homomorphism. So we want to give it a variety structure, and we know G is already a variety, right? Because it's an algebraic group. So we look at the we can embed this home of gamma, the home set into GR product of G through the evaluation map, right? Because gamma is generated by R elements, right? So, and it's a free group, so it's completely determined by the image of the generators. So if you take any row which is a homomorphism, so we can map it to row of gamma 1, and each of them is going to be an element in G. So this gives an evaluation map, which is always an injective map, and it's surjective in this case because gamma is free. We are working over a free group of rank R. Okay, so in this case, they are actually bijective. Home is bijective to GR, so we can since GR has a variety structure, this home gamma G inherits a variety structure from GR. So we can give a variety structure to this set home gamma G. Okay, and now since this is a if it is a variety, then there is a coordinate ring associated to it, right? So it's which means it is the quotient of and the coordinate ring of, so we denote this by C and we write home gamma G in the square brackets, and this is the quotient of a polynomial ring, right? So we have a coordinate ring for this variety, and if gamma was not, okay, I want to mention one thing. If gamma was not a free group, then there will be some relations, right? Which would mean that this is injective, and so this will be home will be a subvariety of GR, and it will be an analytic subvariety, so it will still have a coordinate ring, but in this case it will be the same coordinate ring as GR. Okay, so now we know that G act on home of FG, right? Or gamma, which is isomorphic to GR, right? So G can act on GR by conjugation on each coordinate, right? So that action we can extend to an action on the coordinate ring by in this way. So every element in the coordinate ring is of the form some polynomial plus this quotient, plus the ideal that we are quotienting out with. So this action we can define by in each of the variables we replace it with a conjugate by G. Okay. So this defines, so this action extends to the coaction here to the coordinate ring. And now what we are interested in is basically, this is the object that we wanted to get to, is the invariant ring under this action. So the invariant subring of this under this action, we denoted with the superscript of G here, and it's basically set of all the polynomials in the coordinate ring such that it's invariant under, by the, like the name says, which is invariant under the action by every element in G. Okay, so we have this invariant subring, and this ring is finitely generated since we started out with the reductive group. Since it is finitely generated, we can write it as a quotient of some polynomial ring, say in n capital N variables. Okay, and so this subring will be isomorphic to C T1 to Tn, quotienting out by some ideal J. Okay, so then by the Hilbert basis theorem, this ideal J is finitely generated, which means it's generated by some, say, K elements from chi1 to chi k. And the character variety is that we want, or also so the character variety of which we denote by this notation of gamma G is actually set of all the points in Cn such that it's a simultaneous zero set of J. So what we are doing is, once we get to the invariant ring, we want to find the variety for which this invariant ring is the coordinate ring, right? So that's what we are doing. So if this is the variety, you can see that the ideal of this variety will be J, and the coordinate ring will be this, right? So that is the idea of a coordinate ring. So let me just summarize that to just recall what I said. Seems like I gave a lot of different things. So we started out, what we did was we started out with a home set of gamma G, and then we gave it a variety structure by embedding it inside GR. And then which gave it a variety structure, and once we get a variety, we find the corresponding coordinate ring, which is a polynomial ring mod out by the ideal of that variety, right? And once we have that, we look at the action of G on the coordinate ring, which came from actually the action of G on G to the power R, or the home set. Okay, and once we have this action, we want the coordinate ring, we want the invariant ring under this action, which is set of all the polynomials which are invariant under the action. And then once we have that, we want to compute the variety corresponding to this ring, whatever subring that we just got calculated. And to get that, what we do is we know that it's finitely generated, and then we since it's finitely generated, we can write it as a quotient of a polynomial ring. And once we get that ideal, we find the zero set of that ideal in C over Cn. Okay, so that gives us the character variety, or G character variety of gamma. Okay, so this is the idea. Now let's look at how we do this with the specific case of by giving specific taking specific groups for gamma and G. Okay, so we look at the case when the number of generators for gamma is 2. So we are taking the free group of rank 2, and we are looking at G equal to SL2C, which is the set of all complex matrices with, 2 by 2 complex matrices with determinant 1. Excuse me. So then we look at the evaluation. I will get to in a minute why the explicit description of why SL2C is also variety. So we look at the evaluation map from home of F2 to so set of all homomorphisms from F2 to SL2C, which basically means every homomorphism is basically the image of gamma 1 and gamma 2, which are pairs of matrices in SL2C. Okay, so since, like I mentioned before, since F2 is a free group, this map is a bijection. Okay, and now, so how can we think of this as an affine variety? As a variety, so think of, so SL2C is a 2 by 2 matrix, right? So think of these as the variable. So we can, so if you take a pair of matrices, then you can see that each of them has a each of them has so they have 8, there are 8 entries, right? So basically and the only property, how can we get all the matrices, all the SL2C? So in the first coordinate, for example, all we want is it's a set of all, and so all possible values for each of these xi sub j's, such that this is true, right? This equation is satisfied, right? This polynomial. So if we take this polynomial, we basically want all the complex numbers, all quadruples of or 4 pairs of complex numbers, such that this equation is satisfied. Similarly, for the second coordinates, we have a second set of equations, which is superscripted by 2 to denote the coordinate. And then we look at the equations for such that this polynomial is 0. This is the equation for the determinant, right? So if I had k entries, then, or r entries, then that would just mean we will have k equations here, right? So this is the so basically each SL2C is just a set of polynomials. So since we have 2 entries here, we take 8 variables. So our collection of entries is sitting in C8. Okay. And now, so we know that, so like I mentioned earlier, this is the polynomial, right, that we want. So these polynomial give this variety, right, SL2C, each of this, right? So if we want to find the coordinate rings, and our points we are taking, we have 8 variables, right? So we are looking at the polynomial ring in 8 variables, and we are quotiening it out by the set of polynomials that gives the variety structure on SL2C2, to SL2C squared, right? So this gives us the this is the coordinate ring for this variety structure on SL2C squared. Now we look at the action. So the SL2C act on SL2C cross SL2C by the which is isomorphic to the home set by conjugation, right? So if you take a pair epsilon and eta, which is in SL2, each of which is an element of SL2C, then this is just the action defined, right? And I think it did not. Okay, so and if we look at the which means if we are looking at and this extends to an action here, which is I should write it a little clearly. So what I want is so G acts on polynomial f of rho as f of gamma 1, G inverse, and G rho of gamma 2, G inverse. Okay, and there is plus I here I'm just not writing the I because it's but it's there. When I say F, I meant F plus I. Okay. So then this ring is ring of invariance is finitely generated, and yeah, and this is okay. And this is, so we can write this as I'll show results next, which tells us exactly what gives us the n, this n here. So the idea is, like I said, we look at the ring of invariance, and then we write it as a we find the corresponding variety to this invariant ring, right? So that is the whole idea. Once we find the invariant ring here, what is the corresponding variety of that? So okay, so now Hilbert's null-Stellen sets, that tells us that all the maximal ideals of this ring, so every ring here actually factors into linear factors. So we can actually write them as in this form, T1 minus A1, where Ti's are variables up to Tn minus An, and this pair A1 to An is in the simultaneous zero set of this ideal J here. Okay, but how do we compute this this specific? How do we know what number is n, and how do we know what how to calculate this invariant ring, or sorry, how to calculate this invariant ring and what gives the invariant ring, right? So in this case, there is a result by Fricke-Ward theorem. They were independently found by Fricke and Ward, where they actually talk about how they give an explicit description of these invariant functions, that if we take, okay, here H is, I think I had a slide earlier which said what H is. So SL2C cross SL2C, right? So, and we look at the conjugation action on G is SL2C. So we have to look at the conjugation action of G on this SL2 cross SL2C, and if F is a regular function which is invariant under this G action, then what it says is for every such function F, there exists a polynomial and 3 variables over complex numbers, such that this function F of zeta comma epsilon comma eta, which are, so epsilon is an element here, and eta is an element in SL. So each of which is an element in SL2C, then we can write it as a polynomial of trace of epsilon, trace of eta, and trace of the product of epsilon eta. And also, conversely, if we look at if we take any point x, y, c in C3, there exists a pair of tuples in SL2C cross SL2C, such that x, y, c actually has this form, trace of eta, epsilon, trace of eta, and trace of epsilon eta. Okay, and they have given, if there were, theorem also says that if suppose there were two, if this was not unique, if there was another epsilon and prime and eta prime such that they are equal to x, y, c, then they always differ by, then they are in the same orbit, G orbit of under this action. So this theorem kind of tells us, so this tells us that this invariant ring is actually, so this tells us that the character variety is given by the space C3, and the mapping actually each row that takes to the trace of epsilon eta and epsilon eta gives us the embedding into the space C3. Okay, so that is that gives us the example in this specific case. But in more generally, in the case of more generally, if you're looking in the case, if you're working with free group of, so this was for free group of rank 2 case, right? We were working on F2 So in general, okay, sorry, one more thing. So if you want a reference for this, there is an exposition written by William Goldsman on the theorem of 3K and Wood, where he gave a elementary proof for that for the result. Okay, now if you want to work, if you want to compute the SL2C character varieties of free group of rank R, then there is an algorithm, and there's a paper by Caleb Ashley, JP Burrell, and Dr. Lawton, which gives an algorithm which gives the results and an algorithm along with the mathematical code on how to calculate the generators of the invariant ring for character varieties of free group of rank R to SL2C, all the SL2C character varieties. Okay, so I'll briefly discuss the results, which tells how to. So it's similar to what I said earlier, or what we saw earlier, that this. So we saw here that the trace functions are the that gives the embedding right onto the for the invariant functions. So if we have a free group of rank R, then okay, then again the polynomial in the polynomial ring will be, so this is basically generalizing what we did for the just writing down as a general case for the 2x2 case. Here we have R, so we have 4 variables for each of the coordinates. So we have R coordinates of SL2C here. Each coordinate have 4 variables. So we have 4 R variables here. And then the ideal generated will be like we have a determinant equation for each of the R coordinate. Okay, so there will be R polynomials. Okay, and I'm just going to denote this polynomial ring by this notation for simplification. Okay, and what we want is, so let's look at this. So this is the, if xij superscript k is an element in the polynomial ring, we denoting its projection to the quotient ring with a bar on top. Okay, and what we want in, and so what we are going to, so these are the so we define these matrices, generic matrices, which are, so there are k generic matrices, which are basically the elements here, x11, x22, so x12, x21, and x22. This is the kth generic matrix, and we denote by its image projection onto the quotient with a bar. So xk bar, as this is the generic unimodular matrices. Okay, and now we define the generators. So okay, before that, so what is the ring of invariant, right? So the ring of this is the notation we were using for the invariant ring, right? This is the invariant ring of the character variety, and this is basically we use the notation C of NR for the just to denote the just the ring of invariance in the polynomial ring and not in the quotient ring. And so which means it will not have, it's the C polynomial. We look at the polynomial ring with the variables xij's, and we look at the invariance in the polynomial ring. And if we quotient that out by the ideal I, then we get the ring of invariance for the character variety. Okay, so this ring is closely related to the ring of invariance that we are interested in, right? So there's a theorem by Procesi which tells us that this ring of invariance in the polynomial ring can be generated by the invariance trace of products of the generic matrices. So this matrices that we saw here, this xk's, if we take the products of this, and all of them will generate the invariant ring. And then immediately from that, we can get that if we Gaussian, if we look at the projection of these traces in the quotient ring or the coordinate ring, that gives us the generators for the coordinate ring of the character variety. Okay. And these are the, so basically the trace of the generic product of generic unimodular matrices give us the generators for the coordinate ring of the character variety. Okay. Now, so this actually gives, so here we talked about, so this theorem gives all the products, right? All possible products of the generic unimodular matrices. But so there is actually, we can further find minimal generating set of those. So what we need basically is we don't need all of these products. What we need is we can just take the trace of first individual generic matrices, and there will be R of them because we have R generic matrices. Then we can take the product of xj and where I not equal to j, and the way to do that is we can choose R. Out of R, we just need to choose two of them, right? So there are R times R minus 1/2 so generators, and then we take the product of three of these possibilities where none of them are equal, and there are choose three options to do that. And these actually these are, and if there is anything more, if there are four generators, we can use Cayley-Hamilton theorem and other properties to any further traces. We can use trace identities and Cayley-Hamilton theorem to further reduce down to any of these cases. So basically we can reduce the others, so that the rest of the products are basically redundant. So if you look at the reference that I mentioned earlier, the paper actually gave a nice explanation of why this set is actually minimal generating set for the character varieties. Okay, so for the coordinate ring of the character variety. So this is the paper I talked about, and yeah, that's what I wanted to talk about today. And just tomorrow I'll talk about I want to say one more thing is, so we were working with character varieties over complex numbers, right? So I want to go back into the definition. Okay, here. Okay, so what I wanted to say here is once we have this ideal J, right? What we are looking at the 0 points of 0 points of this variety over complex numbers, right? So if so the variety also comes with an additional structure called sheaf, which I didn't mention here, but which I didn't go into detail. So if these polynomials that we get here, if they are defined over integers, then we can also look at these 0 set of these polynomials over finite fields, right? So, or we can look at the 0 sets even for integers, and once we can look at the 0 sets over integers, we can look at the 0 sets over finite fields, right? So even though we are defining the character variety over finite fields, it makes sense to look at the finite field points of the variety also. So it will be, for example, like when I mentioned the example circle, even the circle, when we draw the circle, we look at, for example, if we are drawing the circle, we look at it in R2, right? This is just R2. But we can also think of, so this is the equation x squared plus y squared equals to 1, right? But, or minus 1 equals to 0. Right, this is a 0 set of this polynomial. But it also makes sense to look at, I can look at the integer points of this or integer solutions of this, right? So in the same way, when it makes sense to look at the coefficients make sense, we can also look at the zero sets over a different field, or even a different ring. So different fields. So it makes sense to look at the zero sets over finite fields and in certain cases. So the research that what I'm doing is actually I work with character varieties over finite fields. So I look at which means that I'm looking at the finite field points of these character varieties, and then I look at the action of automorphism group on these character varieties. So I'll talk about this in detail tomorrow. So thank you for listening. Do you have any questions for me?